So in this video, I am going to be explaining how to use a proportional controller to control the liquid level inside of a third tank in its system of 3 tanks by changing the flow rate into the first tank. So we're going to take a look back at our code for our 3-tank dynamical system that we just did. So we imported all of our initial values and we initialized the value of H naught from this equation. And the only thing that's going to change here is that we are going to have a 10% set point increase in the liquid level of our third tank. So we're going to change this to 10% increase in third tank. So then we define the right-hand side of our equation by finding the flow out of each tank and then finding the differential equations to find the height of liquid in each tank. And then we use solve IVP to evaluate the right-hand side of our equation. And then if we look at our plots down here, we can see that each of the tanks' liquid level height did increase as the flow increased. And after some time, about 1,000 seconds, we reach steady state again. So now we're going to find how to use a proportional controller to we're going to use a proportional controller to control the level in the third tank by stimulating the flow into the first tank. Okay, so now to solve this problem, we want to say that our H3 set point is higher than our original H3, so the height in our third tank. So we can say that our H3 set point, and we can say that we can subtract our H3 from this. So we know that our height is just in the unit of meters, and we want this equation to be in the unit of meters cubed per second since we're trying to compare this to our initial flow rate, or our flow rate into our first tank. So we need to multiply the right-hand side of our equation by some number. So we're going to use Kc, and Kc is just our controller gain, which that's just a fancy way of saying that it's a proportionality constant. So we can set this equation equal to our Qn. But if we think about this, if we just have our H3 set point minus our H3, which should be a relatively small value, multiplied by our Kc, which could be any number, but most likely we're going to use a relatively small value, then our Qn is going to be very small, which is not what we want since we are saying that our Qn is going to increase. So we need to add our Qn naught onto this equation because we're saying that our Qn naught increases by the amount of Kc times our H3 set point minus our H3. Okay, so for this example, we're just going to add on to the code that we used for our 3-tank dynamical system. So we need to start out by initializing our value for Kc. So we're going to use a really small Kc to start out with, but we might change this once we look at the graph. And we also need to initialize our H3 set point. So let's say that we can say that our H3 set point is our H naught times 1.1. Since we're trying to say that we want a 10% increase in our third tank. So now we can compare our H naught and our H3 set point to see the difference. So we can see that our H naught's around 5.1 and then our H3 set point's around 5.6. So this does show that 10% increase that we want. So now we need to change our Qn equation to the one that we just wrote on our whiteboard. So we can say that our Kc times our H3 set point minus our H3. And then we need to add our Qn to this, or our Qn naught. And let me add one more parenthesis just to make sure we have the right syntax here. All right, so now if we control shift down to the bottom, we can see that our plot changes. Actually, let me make this time frame a little bit larger so we can see it better. So now we can see that our tank height is increasing, but we only get to about 5.1. So let's change our Kc value and let's increase it a little bit. So now we can see that we did go a little bit higher, but we're still not close to our set point. Alright, so we are starting to oscillate a little bit here, and we are starting to get closer to our set point little by little, but we're still at 5.35. And the oscillation just kind of shows that when the flow was increased into tank 1, it got up to about 5.5, and then it started to come down because the flow out of tank 1 started to increase into tank 2, and you can see that correlation with tank 2 and tank 3 also. So let's keep increasing our Kc here. So why don't we go to 0.5. So now we can see that we are oscillating a lot before we reach about 5.5, but we're still not at that set point that we want. So let's try 0.9 or 0.9. Okay, so now we actually went too high with our Kc value, and our collab's starting to tell us that we're just going to infinity. So let's decrease a little bit. Let's try 0.08. Okay, so that one works. But now we can see that we are just oscillating, and this is what I was talking about when I said we were just going to go to infinity. This never will, like, I guess this, it won't reach a steady state in the time frame that we have, and collab's telling us that it's just going to go straight to infinity. So let's decrease it a little bit more. Let's try 0.06. So we're still not reaching a steady state again, so let's go down even more. So let's try 0.04 again. So we can see that we do reach a steady state again, but we are at 5.5. So this example kind of showed us that a proportional controller is never going to get you to your exact set point. It'll just get you somewhat close to your set point. But there are other controllers that you can use to get to the set point. We're just not going to go over them in this video. So we can see that if our Kc value is around 0.4 to 0.5, we are still reaching a steady state, and this is about as close as our set points can, or as close as we can get to our set point just using a proportional controller. Thanks for watching.